Be talking about Fermat's theorem, which is a classic theorem in in real analysis. It basically says that if a function, oh, I just deleted all this. If a function satisfies all of these three properties, then we know that the derivative of this function at the point x0 equals 0. Obviously this makes sense, but of course we have to prove it. The proof is very simple, and it's a good practice if you're just getting into proofs, so we have to do them for your class. But basically, first let's talk about these three things over here. What does it mean that x0 is an interior point of the domain F? Well, that just means if we have our domain here, defined on the real number line, and we have our point x0 here, that means that we are able to take an interval, for example, x0 minus delta, x0 plus delta, such that the interval of this x0 is still in our domain F, which just means x0 can't be a boundary point. We can't have x0 like on the boundary, because then again, even if delta is very small, we can't have x0 plus delta would go out of this interval. So our point x0 has to be an internal point of our domain, and that will become apparent why we need that, because we need to take the left and the right derivative. And if our point would be here, we couldn't take the right derivative because we don't know what's over here, it's not defined. Then f has to be differentiable at x0. I mean, that makes sense, because we're going to be working, our proof is going to be using derivatives, and x0 is the local extremum. That just means it's a local minima or local maxima. And what I actually mean by that, well, if I'm looking at an interval, x0 minus delta, x0 plus delta, for delta however small in the domain of f, then basically I'm saying that for every x in this interval, which I can define as being called I, for every x in this interval I, f of x will be greater than or equal to f of x0. If this is the case, then x0 is a local minima, and a local minima, not necessarily a global minima. But that just means again, if I have a function like this, and I'm looking, if I choose this point as my point x0, then again I can see that there exists an interval, x0 minus delta, x0 plus delta over here, x0 minus delta, x0 plus delta, such that this is our point f of x0, and we obviously see that f of x will always be greater than or equal to our point f of x0, because it's a local minima. But then again, it is local. My function can continue like this, and I can have another point which goes even lower, so it's not necessarily a global minima, but we can see that it is a local one, and a local minima, a local extremum is enough. So we will be doing our proof for the local minima, and we'll be using the left and the right derivatives. So first of all, let's take the right derivative, and I'll explain what that means in a second. F plus at the point x0, and that just equals the limit as h goes to 0 from above of f of x0 plus h minus f of x0 over h. Now, what do I actually mean by taking a right derivative? Well, obviously, whenever we have a function, and let's say we're trying to find the derivative at this point, we can have, usually how we define derivatives is the limit as x goes to x0 of f of x minus f of x0 over x minus x0. That is just the classic slope of a tangent. So, we choose a point x0, and then we choose a point x, and x gets closer and closer to that x0, and again, we're calculating the slope of the tangent, y2 minus y1 over x2 minus x1, and eventually as x gets, a point x here, we'll get very close to x0, and we'll just calculate the slope of this tangent, and then we can do this from the left or from the right. So our x can be our x can be to the right of x0, or our x can also be to the left of x0, and again, it's gonna get closer and closer and closer from this side. So and if the function is differentiable at a point, the left and the right derivative should be equal. So if we're taking the right derivative, well then in this case, I'm just defining my h as x minus x0. So if we're taking the derivative from the right, if I have my point 0 here and my point h will be approaching 0 from above. It will always be positive. Here are the negative values, here are the positive values. H will always be positive. It just tells us that our point x, our point x will be greater than our point x0, and it's going to approach x0. So because we know that h is going to be positive, what we can say about this is, well, this will obviously be greater than or equal to 0. And what can we say about this thing over here? Well, this thing over here will also always be greater than or equal to 0. And why? Well, because we said that because x0 is a local minima, we know that there exists an interval. We have our x0 over here, and we know that there exists an interval x0 minus delta, x0 minus delta, x0 plus delta. We know there exists such an interval such that for any x over here, our function f of x, our function f of x will be greater than or equal to f of x0. And because h approaches 0 from above, this over here will be, looking at our point x0 plus h, or point x0 plus h will be somewhere over here. And as h approaches, x0, our point is going to be sliding here, 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 and eventually when x is 0, our point is going to come to over here. So eventually it's going to have to get into this interval. No matter how small this delta interval is, no matter how small of a local extremum or a local minimum it is, even if our function, looked like it got small for very small, it has a very small dip, will still eventually, because h goes to 0, our point x0 plus h over here will be inside of this interval, which means this has to be greater than this, at the limit as h goes to 0. So this will always still be greater than or equal to 0, which means that our right derivative has to be greater than or equal to 0. It has to be greater than or equal to 0. And now, you can probably guess what's going to happen. Now we're going to look at the left derivative, f minus of x0, which equals the limit as h goes to 0 from below of f of x0 plus h minus f of x0 over h. And now, what can we say about h? If we look at our graph over here, this time h will be negative. So again, if we're looking first over here, well, our h is going to start somewhere negative and it's going to be approaching 0 from below, which just means, with the classic definition, we're just looking at a point x here. The x will approach x0, but that just means h is defined as x minus x0, so x will be less than x0, so this point will be negative. So, when this approaches here, x will approach 0 here, it's always going to be a negative value, which again means that this value over here will be less than or equal to 0 in the limit, and this over here will still be greater than or equal to 0, because again, our point, x0 plus, x0 minus h will be somewhere here. I'm writing plus here, but h is actually minus, so it's x0 minus h. And then you go again, as h goes to 0, eventually our point will go inside of this, of this area over here, and any point inside of here, has the property that f of x is greater than or equal to f of x0. So this will still be greater than or equal to 0. However, h will be less than or equal to 0. So our left derivative will be less than or equal to 0, because if you have a fraction and one value is positive and one value is negative, obviously this will be negative. So because the function is differentiable at f of x0, that means the left derivative, f of x0, which is less than or equal to 0, has to be equal to the right derivative, f of plus x0, which is greater than or equal to 0. So the only way that holds is if it's equal to 0. The only way this equality can hold is if the derivative equals 0. So that is how you prove it. It's a pretty clean and intuitive proof. I hope it makes sense. And just one more thing we have to mention is, this, if we satisfy these 3 points, that means this is true. However, this theorem doesn't state that if this is true, all of these 3 points are satisfied. If the derivative of x at the point x0, if the derivative of our function at the point x0 equals 0, x0 is not necessarily a local extremum. For example, look at the function x cubed. We have a stationary point. We have a point here where x0 is, at the point 0 is not a maximum or a minimum, but the derivative of f of x at the point x0 is still 0. But it's a stationary point. It's not actually a local minimum or maximum. So if this is true, then this is true. However, if this is true, these 3 things are not necessarily true. It does not go both ways, so you just have to be careful with that. But yeah, that is Fermat's theorem. Thank you for watching.